In this video, we shall look at a few review problems associated with motion of a center of mass of a system. Before we do the problems, let's look at some essential concepts. Let's assume we have three objects, Object 1, Object 2, and Object 3. They are at some distance from the origin of a coordinate system. Let's assume the Object 1 is at distance r1, Object 2 at a distance of r2, and Object 3 at a distance of r3. So let's assume the mass of Object 1 is m1, mass of Object 2 is m2, and mass of Object 3 is m3. So the position vector of that center of mass is given by the following equation. m1 times r1, r1 is the position vector of that object, plus m2, position vector of Object 2, plus m3 times position vector of Object 3, divided by the sum of all the masses, m1 plus m2 plus m3. From this equation we see that if, let's say, the masses start to move, let's assume m1 starts to move that way, m2 starts to move that way, and m3 moves that way. That means in general, the position vector of the center of mass would also change. That means the center of mass would move when the objects move. That would imply the velocity for center of mass and also the acceleration of center of mass when there is a net force acting on these systems. This is what we mean when we say motion of center of mass. Now let's get to the problems. Problem 1. Each of three particles below experiences an external force as shown. F1 is 4 newtons, F2 is 10 newtons, and F3 is 12 newtons. Find the acceleration of the center of mass of the system. Let's assume this mass is mass 1, this is mass 2, and this is mass 3. So the acceleration of the center of mass is given by the following formula. The mass of Object 1 times its acceleration plus the mass of Object 2 times its acceleration plus the mass of Object 3 times its acceleration over the sum of all the masses, m1 plus m2 plus m3. However, m1 times a1 is just f1, where f1 is that. m2 times a2 is quite simply f2. Likewise, m3 times a3 is just f3. So we have written these f's here. Now let's substitute the numbers. So the acceleration of the center of mass equals f1. f1 is going to the left with that much magnitude. So it's minus 4I hat. Of course, we are using the convention that this is the positive x-axis, so that is the minus x-axis, that is the positive y-axis, and this is the minus y-axis. Now let's do F2. F2 has components. It has x components and y components. The magnitude of F2 is 10 newtons, so the x component is 10 cosine 30 degrees. Now cosine 30 degrees is square root 3 over 2. Likewise, the y component of the second force is 10 times sine 30, which is 10 times half. So the x component goes to the right, the y component goes up. So substituting these numbers, you get 5 square root 3 I hat, that's the x component, plus 5 j hat, which is the y component. Now the last force, F3. F3 has a magnitude of 12 newtons and it's going to the right. So that's plus 12 I hat. And this entire thing will be divided by the total mass. So 4 plus 4 plus 6. So you're getting 14 kg. So the acceleration vector will become 1 over 14. Let's group the I hat first. So that is 12 minus 4, that's 8. So 8 plus 5 square root 3. So that is the second term right there. And now the j hat is just 5, the unit of which is meter per second squared. We can compute the magnitude of this acceleration. This is, after all, it's just a vector. So when you take the square of the components, sum them up, and take a square root of it, you get 1.24 meter per second squared. What about the direction? We note that the x component of that acceleration is positive. The y component is also positive. So this is 8 plus 5 square root 3, and this is 5. So we can compute this angle. Let's call it alpha. So alpha is quite simply arctangent of 5 over 8 plus 5 square root 3. And you get about 16.7 degrees for the direction of acceleration. Problem 2. An object is shot with an initial velocity as shown below, namely 20 meters per second, and the projection angle is 45 degrees. At the highest point of the trajectory, namely here, the object disintegrates into two fragments of equal mass. One falls vertically downward, so the green object, the green fragment, drops vertically downward. How far from the launch point does the second object, or the second fragment, the pink one, land? Assume there is no air drag. The forces that cause disintegration are internal forces. So they are forces that act on one part of the system due to the other part of the system. The net external force that is acting on the system is the gravitational force. Regardless of whether the disintegration occurs. Thus, the acceleration of the center of mass of the fragments remains equal to the gravitational acceleration. This means that the center of mass of the fragments follows the same trajectory that the original object would have followed had it not disintegrated. And this is that original trajectory. Let's call the range of that original trajectory capital R, and this point that corresponds to the highest point is R over 2, half the range, and the range is measured from the launch point. What that means is this is also the location where the center of mass of the fragments land. We know where the first fragment lands, so we assume that the x-coordinate where the second fragments land to be, say, x bar. Let's assume the original object has a mass of 2m. So each of these fragments would have mass m and n, because we are told that they disintegrate into two fragments of equal mass. Since we know the position of the center of mass, namely R, that is this, and center of mass point is given by the following formula. The mass of each piece times where it lands. The first fragment lands at R over 2. The second one also have mass of capital M, but it lands somewhere. Let's call it x bar. That is the point that we want to determine. Divided by the total mass, which is 2m. So you see the m goes away, and we can determine x bar. So what is x bar? In terms of capital R, it is just 3 over 2 r. Now let's proceed to determine the capital R. From projectile motion, we know that the range in such a case is given by the initial speed, which is 20, square that over the gravitational acceleration times sine twice of that projection angle. So in this case is 45, so 2 times 45, which is 90 degrees. So sine 90 is 1, and you're going to get capital R as 400 over gravity. Putting this in here, we will get x bar, which in this case is 61 meters. So that is the distance from the launch point where the second fragment lands. Problem 3. How far from the center of mass of the Earth-Moon system from the center of the Earth? Mass of Earth is given by that number, 5.98 times 10 to the power 24 kg. Mass of Moon is 7.36 times 10 to the power 22 kg. And the distance r between the center to center distance, that is, between Earth and Moon, is given as 3.82 times 10 to the power 8 meters. Of course, we want to measure the distance from the center of the Earth, so let's call that the origin. So let's apply the following formula for center of mass. Center of mass coordinate from a given origin equals mass 1 times its coordinate from the origin plus mass 2 times its coordinate from the origin over the sum of the two masses. So in our case, mass 1 can be taken to be the Earth. So mass 1, we know what the mass of the Earth is. However, this x1 is the distance where the mass of the Earth is concentrated from the origin. Now we know the mass of the Earth is concentrated exactly at the origin, so x1 in this case is 0. Mass 2 is the mass of the Moon, so which we know to be 7.36 times 10 to the power 22 kg. x2 is the coordinate of Moon measured from that origin, so it has to be the entire distance, which is r. And we also know what r is. R is given by that. So times 3.82 times 10 to the power 8. And you divide this entire sum by the mass, the total mass of Earth and Moon, which is 5.98 times 10 to the power 24 plus 7.36 times 10 to the power 22 kg for the Moon, which will give you 4,644,377 meters, which can be rounded as 4,600 kilometers. We note that since the radius of Earth itself, it's about 6,400 kilometers, we see that this position of a center of mass of the system is below the surface of the Earth, say somewhere there. And this is simply because the mass of the Earth is much, much larger than the mass of the Moon. If you found this video useful, please don't forget to subscribe, like, and share. Thank you for watching.